Welcome back to our Introduction to Causal Inference course. In today's video, we're going to continue to talk about the required conditions for estimating causal effects. In previous videos, we already discussed that we need three main conditions or prerequisites for estimating the average causal effect. The first of them is positivity, the second one is exchangeability, and we already discussed those two conditions in previous videos. And in today's video, I want to start talking about the third condition, which is a well-defined causal contrast. And as I already mentioned in previous videos, we can divide this third condition into two components. Today's video is about component one, absence of interference. So what does absence of interference means? This assumption essentially postulates that the effect of the exposure on the outcome in a given individual is not itself influenced by the exposure status of other individuals in the population. So what do I mean by that? For example, take any individual in the population, say individual A, and ask the following question. What is the individual level causal effect in individual A? The answer to this question is completely independent on whether or not individual B, that is another individual in the same population, was exposed or unexposed. So absence of interference implies that the individual level causal effect depends only on individual characteristics. That is, it might depend on whether or not the individual is younger or older or male or female or obese or non-obese or physically active or physically inactive. That is, the individual level causal effect might vary according to characteristics of the individuals because those characteristics might be modifiers of the effect of the exposure on the outcome. And the individual level causal effect can, of course, also depend on contextual characteristics, that is, characteristics to which the entire population is exposed. So those do not contribute to variability in the causal effect within a population, which means that the individual level causal effect within the population depends only on individual characteristics. And therefore, we can define the individual level causal effect without the need to refer to other individuals in the population. In other words, to define the individual level causal effect, I only need to think about that specific individual and not about other individuals in the population. So now I want to discuss a few examples for us to have a more concrete idea of what absence of interference actually means. So for the first example, imagine a population where the coverage of a given vaccine is 0%. There is no one in that population is vaccinated. And we are interested in the effect of the vaccine in preventing the disease in a specific individual in the population, and I'm going to call this individual 1. And suppose that to address this research question, we can implement two interventions. The first one, only individual 1 receives the vaccine. So I vaccinate individual 1 and don't vaccinate anyone else in the population. Or intervention 2, everyone in the population, including individual 1, receives the vaccine. Given this scenario, let us think about the following questions. Is the intervention that individual 1 received the same in both situations? That is, if I consider only what happened to individual 1, is it the same in intervention 2 and intervention 1? And the second question, will the individual level causal effect in individual 1 be the same in the two situations? Now let me propose a second scenario and then we can compare the two. In the second scenario, we are imagining a population where the prevalence of hypertension is 100%. And we are interested in the effect of a pressure-lowering medication on the risk of myocardial infarction, specifically in individual 2, which belongs to this population. And to address this research question, suppose we can implement two interventions. Intervention 1, only that individual received the medication, and in intervention 2, everyone in the population, including individual 2, receives the medication. So notice is very similar to the previous example. In the intervention 1, only the individual of interest receives the intervention, and in intervention 2, everyone in the population, including the individual of interest, receives the medication. And we are going to ask the same questions we asked previously. That is the intervention that the target individual received the same in both situations? And the second question, will the individual level effect on that individual be the same in the two situations? So let us think about the two examples, the vaccination example and the pressure-lowering medication example. In the vaccination example, we know that in general, the higher the vaccine coverage, the lower the risk of an unvaccinated individual to get the disease, and this is called the herd immunity effect. Therefore, the individual level causal effect does depend on whether or not other individuals were vaccinated. In our example, if we were to apply intervention 1, where only the target individual receives the vaccine, the effect of vaccinating that individual on that individual will be much, much bigger than in the situation where everyone else in the population is vaccinated and then I vaccinate that individual due to herd immunity. So there is interference. The exposure status of other individuals in the population does influence the individual level cause effect on a given individual. So now let us consider the other example, the example involving antihypertensive medication. I think it's pretty intuitive that it is less likely that whether other people take the medication influences the effect of the medication. I mean, let's think about it. If I take a pill, is that going to influence the effect of you taking a pill on you? I mean, we could perhaps, create some scenarios where this would happen, but I would say it is much less likely than in the vaccination example. So in this case, there is no interference, or at least much less interference compared to the vaccination example. Okay, we understand what absence of interference means, but what is the problem with interference? Let us try to understand that with a very simple example where we have a population with two individuals, individual 1 and individual 2. And let's suppose we know the potential outcomes for both individuals. But now, because I have interference, I can no longer define the potential outcome only with respect to the exposure status of individual 1, but I also need to consider the exposure status of individual 2. And if I had more individuals, I'll need to take those into account as well. So now I no longer have 2 potential outcomes per individual, but I have 4 potential outcomes per individual in this simplified situation where I have 2 individuals in my population. And the implication here is that I no longer have one individual causal effect for each individual. I have 2 individual level causal effects for each individual. To see that, consider individual 1. So in the situation where individual 2 was unexposed, I have the effect of the exposure on the individual 1 being equal to 1 minus 0 equals 1. But in the situation where individual 2 was exposed, then the effect is 0. And the question is, which one is correct? And the answer is both are correct. But notice that this creates an ambiguity. I no longer have a single individual level causal effect for a given individual. And for that reason, I can no longer define the average causal effect in the way we defined previously, because that definition assumed we only had one individual level causal effect per individual. So in the previous example, in a population of only 2 individuals, we had 4 possible potential outcomes per individual when we had interference. But notice that if we have 3 individuals, we would have 8, 4, we would have 16, and so on. That is, we would have 2 to the n, where n is the sample size potential outcomes for a binary exposure if we have interference. Notice, therefore, that the conclusion is that the larger the population, the more missing data on potential outcomes we're going to have, because only one of them is observed per individual, but the more people we have, the more possible potential outcomes we have. And as I already mentioned, if there is interference, our definition of the individual level causal effect is no longer valid, because this definition ignores the exposure status of other individuals in the population, which we cannot do if we have interference. Given the importance of interference for an unambiguous definition of individual level causal effect, and therefore of the average causal effect, we should be concerned about it. When is interference more likely to happen? I would say it is more common when the outcome depends on social interactions, as in the vaccination example, and therefore whether or not the other individuals were exposed might influence the effect of the exposure on the outcome on other individuals. And those include, vaccination or school-based educational interventions, and etc. In our course, we're going to assume absence of interference, so we can uniquely define the individual level causal effect. But in situations where we think this assumption is unrealistic, one possibility is to model interference statistically. However, doing so often requires very strong assumptions. And in some cases, a simple alternative is to just change the unit of analysis. So for example, in vaccination studies, instead of having individuals as the unit of analysis, we could have, for example, communities, under the assumption that most of the social interactions occurs within communities, so that there is little room for interference between communities. Or in the example of a skill-based educational interventions, we could use school or class instead of individuals, again, under a similar assumption. So what I tried to say in this lecture is that when we have interference, we can no longer define the individual level causal effect without referring to the exposure pattern in other individuals in the population. And therefore, the assumption of absence interference is very useful for us to be able to uniquely define the individual level causal effect and therefore to have a well-defined causal contrast. However, although absence of interference is necessary for a well-defined causal contrast, it is not sufficient. We need the second component of this assumption, which we're going to talk about in the next video. Stay tuned for that.